Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's Design News webinar, Rapid Reverse Engineering, Deep Dive into 3D Scanning with 3D Printing, sponsored by Formlabs and broadcast by Informa. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, this webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, share this webinar via social media outlets, and participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event, and you may also download a copy of the slides via the resources widget. Towards the end of our webinar, we will ask you to complete our survey found on the right-hand side of your screen. Please take a moment to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. And lastly, if you're experiencing any technical problems, please click on the Help widget found at the bottom of your screen and, or type your issue into the Q&A text area, and we'll be glad to offer one-on-one assistance. And now on to the presentation, Rapid Reverse Engineering, a deep dive into 3D scanning with 3D printing. Discussing today's topic is Faris Sheikh and Amos Dudley. Faris, webinar specialist at Formlabs, has helped Formlabs run over 40 live broadcasts around the world to educate over 21,000 engineers, manufacturers, dentists, and jewelers on how to successfully incorporate Formlabs products into their day-to-day workflow. Amos, applications engineer at Formlabs, dedicated to pushing the boundaries of functional 3D printing by integrating synergistic manufacturing and design processes. To learn more about our speakers, please visit the bios widget. It's with great pleasure I now turn this special session over to Faris to begin. Faris, take it away.
Thanks, Chris. I just want to emphasize at any point in today's presentation, please ask questions while I'm speaking. We're going to have a dedicated section for us to discuss Q&A at the end. Amos will be here to help out with those questions and answer some specifically tailored questions you might have as well. Thank you all for joining today. I'm happy to see you all here. And my hope today is that you're going to learn basically a step-by-step reverse engineering process for installing an aftermarket digital gauge. So before today, you might be experiencing some of these things. You might be experiencing downtime waiting for OEM replacement parts for some of your tools. Maybe you are familiar with precise measurement and you've been constantly manually measuring things, but it's been a roadblock for you to reverse engineer some complex parts. Some of those complex parts were not easy for you maybe to measure. Or maybe actually you're kind of just more curious overall about 3D scanning and the tools on the market. So there's a large confusing field of options out there, and you might just want to know where to get started. So my hope is after today's presentation, you're going to be able to replace broken parts by scanning and digitally restoring them. You're also going to be able to extend functionality of existing machines via an automated reverse engineering workflow that I will teach you. And you'll have some recommendations on where to start with 3D printing technology, 3D scanners, and how to navigate the different options you have to consider out there. So really quick look at today's agenda. We're going to discuss who is Formlabs, if you don't know who we are. We're going to go into introduction of 3D scanning. What is it exactly, and what is reverse engineering? And then we'll go step by step how you can 3D scan and print. We're going to go through an example. I'm going to show you. It's a part inside of a car and a vehicle, and we'll go through that whole process. And then quickly teach you about how you can choose a 3D scanner, and then give you some next steps. And then followed by a Q&A. So really quickly, who is Formlabs? So we're known for creating reliable, accessible 3D printing systems for professionals. Specifically, we've been known for releasing stereolithography 3D printing in the past decade or so. And here's a picture right here of Max Lebowski. He is the CEO and founder of Formlabs. Back in 2011, right here actually in Cambridge, Massachusetts, he had a vision. Him and two colleagues. He wanted to create a desktop-sized stereolithography printer because back then they were industrial and huge, but he wanted to not only make it small and a smaller footprint, but make it very affordable and accessible and easy to use. And we delivered on that promise ever since. Formlabs, came out with the initial product, the Form 1, 2012, and we've iterated on that flagship product and printer ever since, coming out with the Form 3 printer this year, some months ago. And to date, we've sold over 50,000 printers in the wild. People are using these printers everywhere. And yeah, all sorts of different cool applications. And with those 50,000 printers out there in the world today, globally, people have printed over 40 million parts. These are 40 million real parts used across so many different industries, from engineering, manufacturing, to dental, jewelry, healthcare, and more. And some of those cool applications you can see in this curve here. The cool thing to see that you notice is the range of applications for 3D printing have been growing. So historically, prototyping, that's been the main case for it. But you can see as the hardware improves, as the material science improves, you get different applications like using 3D printing for anatomical models, creating clear aligner models. Then for hybrid production on the factory floor, you can create replacement parts, you can create customized tooling, jigs and fixtures. And then as that material science really improves, we're seeing production level use cases like general purpose plastic parts, 3D printing actual dentures that you can put in your mouth, and even parts for athletic shoes that you could wear today. Quick example of some of those customers out there and some of these applications. We have Google ATAP here. Really quickly, they were kind of dialing in on the overmolding processes for a wearable component. Instead of outsourcing, which would have taken them weeks, they were able to create this PCBA insert using our high temperature resin, and then saved over $100,000 in the process, and doing that in-house with a couple of Formlabs machines. Another really cool example is Razor Maker by Gillette. So Gillette was able to unlock an entirely new business model, and you as a consumer can go online today and order a customized razor handle, choose from 48 different designs, and even customize your name on the handle. And these handles are all 3D printed on Formlabs machines. So at Gillette headquarters, they run a fleet of Formlabs machines to print these round the clock. And that's only possible due to the freedom of mass customization, which has been enabled by 3D printing. Stranger Things, it's been really hot. Some of you might know, at least people I talk to all the time, Stranger Things Season 3, everyone has been binging that. And so this scary looking creature right here in the middle, that model was designed digitally, and traditionally they would kind of outsource it to kind of print that model out and then paint it. Instead, the agency that actually did all that work, Aaron Sims Creative, it's that logo right above Stranger Things, they decided to actually bring in a couple of Formlabs printers in-house, designed, made some tweaks, printed the model the same day, and was able to show those models to directors in meetings. And lastly, we launched this new partnership with New Balance. So we actually have a part of a shoe on their new triple cell series of shoes. This part, this heel sole here, was actually 3D printed using rebound resin, which is a custom formulation we developed with them. It essentially allows for high elongation, high energy return. It's a pretty interesting thing that shoe companies are doing out there. Essentially, if you have maybe sneakers on right now, the sole is made out of EVA. And EVA doesn't perform too well after hundreds of miles of use. So these companies, shoe companies, are really looking into new options like rebound resin to basically make the shoe last longer, so runners don't have to replace them after a couple hundred miles. So yeah, those are some examples of kind of what we're doing, and it speaks to our mission statement. We're expanding access to digital fabrication so anyone can make anything. And now I'm going to jump into an introduction of 3D scanning and reverse engineering. What are 3D scanners? They're machines that can measure complex objects as easily as simple ones. Compare that to the machine of the human body and manual measurement. Manual measurement, with this example in the photo here, that custom duct that you see that's kind of triangular looking, that custom duct, if you were to manually measure that, that would take you a lot of time. There's so many different curves and features you have to account for. For example, though, if you were to compare that to, let's say, a 5x5 block, that would be so much easier to measure and quickly reproduce. Not the same with that custom duct, and that's where 3D scanners really have that power. They can measure these complex objects as easily as simple ones. The same amount of time it would take to scan that, they could do a simple 5x5 block. And I equate this convenience, this digital kind of convenience, to the technology of 3D printing. 3D printers can do the same thing. They can manufacture complex objects as easily as simple ones. So for example, take a look at that same custom duct here. We were able to kind of print this duct in the same amount of time if we were creating another object with the same amount of material and volume. Compare that to traditional fabrication. Let's say you're machining a component. The time it takes you to machine a component can take you a lot longer depending on the geometry, the number of undercuts and overhangs you're accounting for. Whereas with 3D printing, the same amount of volume of an object would take the same amount of time. So that's really the beauty of a scanning to printing workflow. They're kind of almost made for each other. It's like a match made in heaven. So that's what I'm going to talk to you about really quickly here is 3D scan to 3D print workflow. There's really two routes. There's replication. So this is, for example, I wanted to take an existing object today and I want to replicate it. So let's say I want to take a prototype for this remote here. If I want to reproduce this remote maybe 10 times, I can go with replication. And that workflow is pretty straightforward. All you got to do is 3D scan this remote prototype. You can make some minor tweaks, like maybe you can add some numbers and some labeling to keep track of the different prototypes. And then you just 3D print it. It's that simple. As long as you have both equipment, you can do that. But let's say you wanted to make some more structural changes to the remote prototype and you wanted to move some components around, or you just didn't have access to the original CAD file and you're making some sort of upgrade to a product or maybe making a jig out of that product. This is where you need reverse engineering. And that process is a little bit more complicated. So step number one is the same, you 3D scan the object. But step number two is you reverse engineer that object to get that CAD file so you can make those structural changes. And the third is you can make those minor tweaks and adjustments and add embossed labels and text and whatnot. And the last step would be the same, which is 3D printing it. So what happens when you scan an object? The output of a 3D scanner is a mesh model. And mesh models are exactly the same kind of file format that 3D printers accept. And this is commonly referred to as a .stl file format. And what a mesh model is essentially it's a surface composed of many, many triangles. And a mesh model does not actually contain any information about the object itself. It doesn't have any information about the components within the object. Rather, it contains the position information of the triangles that overall define the shape of the object. Compare that to solid models, and many of you might relate to this today. Solid models do contain information about the object. So for example, let's say that inner wall in this model here, if we wanted to double the height of that wall, the other components around the object would adjust and accommodate that change because solid models contain information about the object and the features. And our goal here is we want to make these mesh models editable, the same way solid models are. And to do that, that is the process of reverse engineering. So let's jump into that, how to 3D scan and 3D print step by step with reverse engineering. So let's look at this beautiful Volkswagen Golf. I think it's a 2018 vehicle. Don't quote me on that. We're going to scan an object inside in this car. So you see this digital gauge in this air vent in the vehicle. And let's say you want to install a new digital gauge in this air vent for maybe a line of cars and need to repeat this process again and again. Let's create an assembly jig to help us do that. So if we want to install a new digital gauge in this air vent, we'll need an assembly jig. And there will be two components in this process to make that assembly jig. It'll be the 3D scanning workflow and the 3D printing workflow. And I'm going to go step by step for each of them. So for 3D scanning, step number one is to prepare your object for scanning. This requires you to basically spray this temporary matte powder all over your object. For slightly glossy surfaces, this is going to improve the dimensional accuracy of your scan. Even let's say you had a transparent part or like a reflective part, this is 100% necessary. You need to spray this powder so that the scanner can really pick this object up. We used our spray from 3dscanspray.com, so feel free to check that out. Second step of the process naturally would be to then get a high accuracy scanner to scan important sections of the part. In this picture here, I'll dive into this later. This is a Next Engine, I believe 3000 scanner, and it's being rotated right now, and it took, I think, under a minute to scan this whole part on that tabletop axis there, so it'll rotate around and scan the whole part fully. Generally speaking, for a part of this size, we recommend a high accuracy tabletop scanner of 100 plus or minus 100 micron accuracy. So that's what we used. The output of that scanner will be a mesh model like I described earlier. Now, the tricky thing with this is that generally speaking, scanners will output mesh models that are huge. The file size is very large, and if you import that into your reverse engineering software, let's say SolidWorks equipped with some plugins, it'll slow down it is a good chance it'll slow down your computer by a lot, and it'll be almost unmanageable to make the edits you want. So what we need to do is a step before that. We need to reduce the file size so that we can make it easier on ourselves to edit this model in CAD. We don't want our computer overheating. So this is the refining the mesh kind of process, and I'll explain what that means. There is a free tool out there called Mesh Mixer by Autodesk. You might have heard of it before. You can use that to easily reduce your file size. And I'm going to show you guys a quick video tutorial of how we did this. So we'll jump into that. All right, so in this tutorial, you're going to open up Mesh Mixer and import your model, your STL file in here. I've done that already with the import feature here. And for this demonstration, I've imported this pulley here, you can see, 360 degrees. It has fairly flat features, and it's not too complicated of a model. However, once we look at this in its wireframe view, you can see really the number of triangles that are composed in this mesh, and that is highly dense, as you can see. I can zoom in right now just a little bit, and you zoom in more, you're seeing thousands, actually hundreds of thousands of triangles here. That's far too many, because the geometry of the model can still stay intact if we reduce the number of triangles by a lot, actually. So you can see in the bottom right-hand corner, we have 772,000 triangles here. Mesh Mixer makes this really easy with their reduce feature. So if I select the object by Command-All on my Mac that I'm using, I can then click Edit and then click Reduce. Now, once I do that, it's going to automatically actually calculate and reduce this file based off the default setting. There we go. It reduced the size. Not by a lot, though. You can still see it's quite dense. So if I zoom in again, it reduced it by about half the number of triangles. On the bottom right-hand side, the number there is not reflective until you click Accept. But we can reduce this more. There's 3 ways that you can do this by reducing targets. So if I click the top feature here, the 2 I'm going to recommend is reducing it by percentage and reducing via triangle budget. So by percentage, we can do something like right now it's at 50%. If we bump this up to, let's say, 90%, you're going to see an impact. So it's computing. There you go. By bumping that percentage up to 90%, it significantly reduced the number of triangles, but also kept the geometry intact. Looking around, it looks pretty good. Another way you can go about this in Mesh Mixer is you can actually select certain parts of the models. Since this area is a flat area here, I can actually use a brush mode to select parts of the model. So I can click, click, and click. And maybe make the brush size a little smaller so I don't get into the curved areas at all. And this is just to demonstrate. I can do that feature again with reduction and reduce, and this time even I can go into triangle budget and try that out. So let's see what happens there. The triangle budget right now has been set to 1,000 for what I selected, but we can reduce that by a far greater amount, far less amount actually. So we can bump this down to maybe even 100 and see what happens. There you go. You have 100 triangles here. Hasn't really changed and hurt the geometry in any way at all, since this is supposed to be a flat part. And I can click Accept. And you can do that for various parts of your model if you're having trouble in using the automatic reduction feature. So once I go back, you can look down at the bottom right-hand corner, and our file has only now 76,000 triangles instead of what it was earlier, which was 700,000. And this should load much easier into your CAD program of choice when you're doing your next steps. Great. Well, I hope that video explained how you can reduce the file size in Mesh Mixer. Feel free to type in questions and let me know questions you have. I see a couple coming in already. Please ask more as this presentation goes on so we can appropriately help you. Great, so now that we've made the file much smaller, we can import that mesh model into our CAD program of choice and then adjust, we can import into our CAD program of choice with loaded in our reverse engineering software. So one of the examples of the softwares that you can use is GeoMagick for SolidWorks. So if you have a complex part with many different curves and it's maybe some sort of organic features or it's an organic model, this is a great tool to use for that. If not, maybe your part has some more flatter features. A lightweight alternative is Extract 3D add-in for SolidWorks, and it's a lot cheaper as well. So that's a good option for you to use. So now the step is to kind of adjust your model with other parts you might have that you might be working with into proper view directions. And now we're going to jump into step number 5 of this reverse engineering and 3D scanning process. We're going to extract the important surfaces we need from this mesh. And there's really 3 ways to go about this, and I'm going to go into all of these separately. The first is manual redrawing. So if you have simpler features, you can kind of manually redraw them by using the scan model as a reference. So let's say, for example, a couple of examples here. For bosses, holes, and pockets, you can easily manually redraw these. This reminds me of just kind of like stenciling. So you see this fun little Pikachu example here. You have the Pikachu drawing here that's been printed as a reference model, and you're able to manually redraw over it. So same exact concept, similar kind of idea. What's good about reverse engineering software is that it provides you the ability to create sketch planes aligned with flat surfaces that helps you with the manually redrawing process. And you can even extract cross sections that match specific shapes of the part to help you while drawing. So manually redrawing will not always work for many sections of your part, especially for complicated curves and complicated surfaces. So we have a couple other options we can kind of look at here. The first is automatic surfacing. So automatic surfacing is a feature that will automatically generate a solid model out of any watertight scan. And a watertight scan is essentially a mesh model that doesn't have any holes in it. So if you took this mesh model and dipped it into a bucket of water, no water would be able to seep into it. And there you go, ta-da, like the automatic surfacing feature will create that solid model. So if you wanted to kind of do some basic add and subtract features in CAD, with this you can. But if you wanted to move around some basic features of the model or make some other adjustments or structural adjustments, you wouldn't be able to. Another example, another kind of thing with this feature is you can look around the edges of this air vent here that's been constructed, and we've lost some sort of dimensional accuracy with this. You can compare that if you look at the mesh model itself. So you can see that the bottom right-hand corner, it's not as smooth as it should be, and we've lost some of the accuracy we wanted. So because of that, we have the third route. This is a semi-automatic surfacing route, and this is what we ended up choosing. It takes a little bit more, it's a little bit more of a learning curve. It takes a little more time. But once you get the hang of it, this is the useful, most common way to extract important surfaces in a precise way. So what this feature does is it generates surfaces that fit to detected regions of the scan. So this purple shaded area here was a detected kind of area that this feature kind of figured out. And I'll kind of show you what I mean by that. You can change the sensitivity settings of this by using a slider. So if you made this, if you move the slider to a higher position, you can find more smaller kind of detected regions of the scan and smaller, finer details. Whereas if you kind of decreased it, it would do the opposite. Here's a video animation of this in process. We pressed that button, it found all these different multicolored shaded areas on the scan. Now what we're gonna do is we're gonna zoom in and start selecting these patches, those red patches you see, we're manually selecting them. And now what we're gonna do is tell the software, hey, consider all these red patches as one plane and one surface that we want to extract. Because this air vent, you can't see it in the model, it's a specific kind of curve. And we're trying to redraw that curve in plane. So if we tell the model that these are all connected, it'll be able to extract that curve automatically. So that's all we need to do, and there you go. You see that kind of yellow tinted surface there. It extracted that surface for us and kind of drew that plane. And there we go. We were able to create the most complex curve of the model using semi-automatic surfacing right there. Now the next step is we're going to trim around that surface based off of the shape and design of the air vent on the edges, now that we have that surface. And there you go, you can see that trimmed surface right there. And now we got to create the different parts of this air vent. So the second wall on the left side here you see, all we did is we basically redrew that curve from top to bottom and extruded it outwards. That was the second step. And we repeated that over and over again, many times. Didn't really have to use the semi-automatic surfacing feature again because the first surface was the most complicated one to kind of extract. We just went through normal redrawing and extruding walls to get what we need here. And once you do that a couple of times, you can trim and then knit all those surfaces together. And voila, there you have this solid model that you just extracted completely. So now that the model is a solid, we're going to use this to make a jig. This is what we're trying to do at the end of the day. We're trying to create an assembly jig so that we can install a digital gauge. To do that, we need to use the solid model so we can manipulate the information of that object to create the jig. Here's a quick example. It's not of the jig itself, but same exact concept. You have a chess piece here, taking a block. We're extracting the chess piece out of the block to create the jig. So we went through that process and made some minor adjustments, and here we go. We have the assembly jig right here. What's great about this, you can see, is this assembly jig conforms to the shape of the air vent. Now, by using reverse engineering to perfectly conform around this air vent, we've created a really stable jig. This jig will really offer us stability every time we use it. So we can go from any angle to install a digital gauge and have a highly repeatable and accurate process for us at the end of the day. And I think that is probably the biggest benefit when we're thinking about reverse engineering and applying that concept to other areas of your day-to-day lives. And many of you all said that you're using metal machine components or considering to reverse engineer them. So that's, I think, what's really great here. So now that we've been through, the 5 different steps for 3D scanning, and we have this jig ready as a mesh file, you can export it as a mesh. We can just 3D print it now. So I'm going to go through a really quick overview on how you can 3D print this assembly jig. So the example I'm going to show you in 3D printing is based off of a type of printing process known as stereolithography. Specifically, what I'm going to show you is a low-force stereolithography 3D printing process. If you're not familiar, what stereolithography is, shorthand is SLA. It's essentially using a laser to cure liquid resin layer by layer to fabricate your part. So you see that module moving from left to right, that is what's it called, the LPU, and has a laser inside of it. And that lighter blue is liquid resin, and we're basically curing a layer by layer and building the part onto that build platform, which is going up and down. And that's how you 3D print using SLA. And there's 4 steps for this SLA workflow. These 4 steps are generally the same for any SLA 3D printer, not just ours, which is the Form 3. So this will apply for other SLA printers you might be evaluating. First step is choosing your material. So at Formlabs, we have a lot of materials. For this specific example, I really recommend using the rigid material. This is a glass-filled resin that offers high accuracy and stiffness. So it's really great for thin-walled features like that custom duct you see, and it's going to be great for this assembly jig as well. That's what I wanted to mention, actually, is that with rigid resin, you're getting the high degree of accuracy, which is really useful in the reverse engineering process because at the end of the day, the main goal is accuracy. So once we've picked that rigid resin, there's 3 other steps. Second is to prepare our design. So there's a little bit of a prep phase generally with all 3D printers. We've made it as easy as possible using our free preform software. So it's a software that will automatically generate some supports as needed. The prep phase didn't take us more than 3 to 5 minutes for this model. Once you're done, after 5 minutes, your model is ready to be sent over Wi-Fi to the printer. And that's the 3rd step. It takes about a minute to assemble your job on the printer. It's a plug-and-play machine. And then it goes off printing. And our assembly jig was printed for a number of hours. And then we get the part from the printer. And the 4th step is post-processing. So when post-processing, what's interesting is that it's almost always necessary with SLA printing. This is because you need to, the part was made with a liquid resin originally. So you need to wash the part and then sometimes cure it. And so there's a little bit of washing and curing steps. If you have these automatic machines, end user time for me is like 3 minutes. It'll take 15, 20 minutes to wash and cure them, and then you'll be ready. Excuse me. And here we go. That's what came out of the whole 3D printing workflow. Here we have our white assembly jig here with the air vent inside of it. And this assembly jig was printed using a printer. We obviously made some minor adjustments. We added some mounting holes on this and made it a little bit more curved around the edges here too. So it looks nice. And there you go. You have your assembly jig, so we can easily install the digital gauge into the air vent and do it in a repeatable process from any angle and in a stable process as well. So hopefully that sheds some light on our reverse engineering process and how you can apply that for yourself with various machine components or plastic components that you're trying to reverse engineer. For other folks here today who don't have a 3D scanner, since about half of them doesn't have a 3D scanner, I'm going to quickly, in a couple minutes, show you how you can evaluate some options out there. For everyone else, please maybe use this time to type in some questions you have on the process. Amos is here with me right now, and we're going to cover those questions soon. So let's jump into really quickly how you choose a 3D scanner. So 3D scanners, there's really like 3 criteria that you have to consider. The first is accuracy. So accuracy is pretty important because it correlates usually with the cost of the machine. The more accurate your scanner, the more easier it's going to be to manipulate and reverse engineer later on. The second is coverage. So a 3D scanner can only scan what it sees, right? Think of it as like human eyes. It can only scan what it sees. So if it doesn't see a specific part, it's going to show up as a hole in the mesh model. And that won't be great. So you want to make sure you have good coverage with your 3D scanner. And lastly, there is cost. So like I mentioned, cost is highly correlated with accuracy. And that's something you always have to factor in with technology. So something you should consider. For very small engineered parts, you really can't beat the options on the dental market for 3D scanners. I know it might not sound like the best fit for you, but if you're looking for really highly accurate parts and they're under 10 centimeters, like the 3Shape E1 is a great machine. Dental 3D scanners have been around for a long time for scanning dental models, clear aligner models, etc. So this technology has been really refined for a very important use case. This clocks in at about like $10,000, and it has a scan accuracy of 10 microns, which is very, very accurate. For parts that are slightly larger, you can use the Next Engine Ultra HD machine. This is what we pictured earlier in our workflow. Is what we used to scan the air vent. It comes with multi-axis support, and it does its job really well. It is a little bit outdated in terms of its user interface and its design when you're kind of working with the software. but it does well at the end of the day. Has about a scan accuracy of 100 microns and costs about $2,900. Third example here, maybe you want to scan a part of a larger machine or just larger in general. You could use the HP Structured Light Scanner Pro. So you have this sliding rail over here, so you can move the camera back and forth and adjust it as needed. Here's a picture of it actually in action here. So you're scanning a larger, I believe, engine part of a vehicle. And you can see how the guy can adjust the movement of the scanner as well. So this has about 50 micron accuracy, comes in around $3,500. Lastly, if accuracy is not that important for you, so for example, low accuracy scanning of ergonomics, and there's some other interesting use cases with this, you can use a handheld scanner, which will affect the accuracy because where your position of your hand is in relation to the object with the scanner will change over time, not always be the same. But it could be a useful use case for you. So it's like $500 for this handheld scanner. So hopefully you got some information on some options out there for choosing a 3D scanner. We have even more information on more scanners you can look at. We have a white paper and blog post on that. It's called How to Choose the Best 3D Scanner. I will link this to you in an email from me. Look out for an email from me after this broadcast. If you have a scanner already and now you're interested in kind of like the digital fabrication process and you're thinking, well, if I can easily replicate objects or reverse engineer and print those objects, you can get a free part printed on the Form 3 today. Since you attended today's webinar, even for people who don't have a 3D scanner, I'll give you a free part. This is a butterfly part printed in gray resin on this Form 3 here. So we have a little 3D printing factory producing thousands of these, that can produce thousands of these all the time. So we'll send you one of these with the supports on it so you can feel the surface quality and accuracy yourself. Look out once again in the email from me.